Thank you. Hello, everyone. I'm Corbin. I work with the MoMA Lab at NYU Abu Dhabi, and I'm an undergraduate. So I'll be presenting ICSQuartz, scan cycle aware, and vendor-agnostic fuzzing for industrial control systems. So with critical infrastructure and industrial control systems, there's a lot of security concerns, as you can imagine, and that's what our paper focuses on. So you can see on the far left is critical infrastructure, your power plants, your water treatment facilities, etc. And then in the middle is the operators that are actually controlling what's going on in these systems and monitoring them. And then on the far right, you can see the actual PLCs, or Programmable Logic Controllers. And that's what our research actually focuses on. It's these little boards that are actually running a lot of the core logic that makes these systems function. And as you can probably imagine, these systems are prime targets for attack. One of the most classic attacks that I think we've all probably heard about is Stuxnet, where the US came up with malware that attacked Iranian centrifuges. Since then, amid rising geopolitical tensions, we've seen a whole plethora of constant attacks. Most recently, there have been a lot of water and wastewater attacks. Also with Ukraine, ICS has been quite the target. And so understanding all of the political situations that perpetuate this threat, it's important to understand actually why are these systems vulnerable in the first place, and what can we do to actually tackle this issue. So one of the first reasons to understand is that operational technology, or the systems that are actually running these PLCs and just in critical infrastructure, have actually merged with information technology. And what that means is that these systems are no longer just running small programs on small boards. They actually have full-fledged operating systems with full-fledged memory vulnerabilities, so software supply chain attacks, all of the regular fun vulnerabilities that you see in IT. And furthermore, you also have remote monitoring capabilities and remote control for emergencies, and all of this also means that a lot of these devices are connected to the internet, and they can now be attacked not just locally, but globally. And finally, ICS software is written by humans who are imperfect, and all of this combined means that ICS software has quite a few bugs and potential vulnerabilities to be exploited. So acknowledging all of this, the rising threat, and also the fundamental security challenges, what can we actually do about it? So how do we detect these vulnerabilities before they're deployed? Software fuzzing is one of the best ways we know of detecting vulnerabilities. In the case of ICS, we take inputs, which are sensor values, and then we send those to the program to be executed. In the case of ICS, that's the control logic. And that produces coverage and crashes. So coverage, if you're not familiar, is just the paths that particular input executes down, if statements, conditionals, etc. And then your crashes are usually prime candidates for vulnerabilities and exploits to arise. So what's out there now, and what are the limitations? Well, there's two works that we compare with. One was a RAID paper, and one's a Usenix paper. They're both, one's called ICS Fuzz, and one's Field Fuzz. And they're state-of-the-art ICS fuzzers, but they're primarily black box. Essentially, they use proprietary compilers, which produce proprietary executables. So rather than your traditional fuzzers that usually produce like a ELF binary or a binary with a compiler that's been instrumented to add all of this extra white box functionality, these are much harder to fuzz. And they're typically vendor locked, because all of this engineering has to go into making sure that it works and can deliver inputs to these proprietary configurations. Another issue is that they can often be imprecise. So for example, both of the state-of-the-art fuzzers that we compare with don't have an address sanitizer. And what an address sanitizer does is it lays out the memory in your program so that if you do an out-of-bounds read, it will actually throw an error. These fuzzers depend on if an out-of-bounds read is so out of bounds that the operating system catches it and it's a segmentation fault. But not all memory vulnerabilities actually cause segmentation faults. And the last thing is no scan cycle awareness. So with ICS programs, these programs actually have this whole stateful nature where it receives an input and then it acts upon that input and modifies a state. And then the next input is received, and it modifies that previous state left by the previous input. And so continually, it gradually builds up the state. So actually testing all permutations of inputs isn't enough for evaluating if a program could or could not have vulnerabilities. You have to test all states with all input permutations. So what do we propose to overcome these issues? I highlight this fuzzing framework that we came up with. Everything in white is things that were existing, and things in yellow are our contributions. So as part of the compilation pipeline, you have input structured text, which is one of the languages, the language that we focus on for ICS programs. And we have some compatibility layers to make it more plug and play. Then we use this open source ICS compiler called Rusty, and we modify it to add code coverage instrumentation and an address sanitizer to be able to more precisely identify vulnerabilities and how well our fuzzer is working. Then that compiler outputs this intermediate representation, which is compiled, along with a backend that maps in some compatibility, the code coverage runtime, and the address sanitizer runtime. Then going to the fuzzing stage, we take that intermediate representation and we also automatically generate a harness so that it's easy for operators to plug in their input programs and they don't have to come up with extra code that actually just helps the fuzzer run. And then we produce the fuzz target. And finally, we use ICSQuartz, the fuzzer that we developed, to actually start fuzzing the input programs. A nice thing about this framework also is that you don't necessarily have to use ICSQuartz. You can plug in almost any other fuzzer that also uses LVM. So AFL, AFL++, libfuzzer, hongfuzz, all of them can also play here. And then that finally produces your fuzzing corpus and your fuzzing solutions, which are coverage and crashes. Then you can run whatever type of security analysis you want using your favorite security tools, GDB, Ghidra, et cetera. And you can also cross-validate vulnerabilities. So potentially, if a vulnerability is actually just a bug in the compiler, then this cross-validation step helps you ensure that, oh, this vulnerability actually does exist also on vendor PLCs. So how does this system perform? Well, we compare our fuzzer, ICSQuartz, with the state of the art. And as you can see, we outperform them in execution speed, time to first crash, and inputs to first crash by over an order of magnitude. One of the biggest reasons for this is that we have detached the actual runtime and vendor requirements from the actual fuzzing. And so instead of having to fuzz on one of those small PLCs that you saw, you can fuzz on just regular server hardware. The fastest CPU you can buy will increase your execution speed. Then also inputs to first crash, because we based ICSQuartz on the fuzzing strategies in AFL++. There have just been improvements. But because of that modularity, as more fuzzing improvements come in, more mutation strategies are developed, then this area will also continue to improve. Then we also added a few mutation strategies that investigate that scan cycle mechanism that I talked about. And we run ICSQuartz against state-of-the-art fuzzers. ICSQuartz is compared against AFL++, Field Fuzz, and ICS Fuzz in some benchmarks that introduce vulnerabilities into programs that are stateful. And as you can see, ICSQuartz is consistently able to identify vulnerabilities across 10 trials that none of the other fuzzers are able to. And we tested this for statistical significance. And we also enable and disable these mutation strategies to make sure that that's actually what's allowing us to detect. And yeah? Oh, 2 minutes? OK. Finally, impact. So we ran ICSQuartz against a 61 ICS binaries from an open source library. And these are some of the highlights. So programs that are italicized were actually a vulnerability we found in the ICS compiler. And then the one in bold is one that was a memory-related vulnerability in this month-to-string function. This notably was only found by ICSQuartz and not by FieldFuzz or ICSFuzz because it was a out-of-bounds read local to the program and didn't cause a seg fault, but was still a vulnerability, and we reported this and received a CVE. So what are the key takeaways from ICSQuartz? We developed the first native fuzzer for ICS programs that surpasses black box state-of-the-art solutions, and we provide this increased precision for code coverage and vulnerability detection. We introduce novel ICS-specific scan cycle mutation strategies that detect vulnerabilities, and we also release these benchmarks to the community. Finally, we disclose the first, to our knowledge, what we could find, structured text CVE, and we discover a compiler bug in the rusty ICS compiler, and that is now patched as well. Thank you, everyone, for listening. You can find the lab website and also the project GitHub above in the QR codes.
All right. Anyone has a question for our speaker? Don't be shy. Well, okay. Thanks again for your talk. Actually very interesting, interesting work. I have a couple of questions. So you use the compiler to inject coverage tracing and sanitizer, and for a specific PLC, if I'm correct.
For a specific language.
Okay, for a specific language.
Yeah.
How difficult is to port this approach to other languages in industrial control system?
So another language that's commonly used is, I think, called function block diagrams, and that one's a more like visual language. So the language we used is more like your C programming languages. You have pointers and every arrays. With the function block one I just mentioned that's visual, there are actually tools, I think, all of the ICS languages that are spec'd out by some of the official bodies are supposed to be interchangeable, and so you can translate them using tools between each other. So it should be relatively trivial to export a project that's built in more of like a graphical language into structured text and then go from there. Yeah.
All right. And, okay, so it's only mainly an engineering problem, right?
That part is that part's more engineering. The scan cycle, like mutation strategies, is more of the novelty that we focused on.
Yeah, absolutely. And then I have another question, because in the paper you mentioned that you are reusing some standard library, let's say glibc, that are de facto used underneath for actual PLC code.
Yeah.
Could be different version a problem, maybe not fully reproducing the logic or finding wrong bugs?
Yeah, it could potentially add in false positives. So that's why, like for the one vulnerability we found in the month-to-string function, we had to cross-validate it on a development board to ensure that it's actually a vulnerability on that board. And it would also be interesting to compare between like firmware versions or between vendors, just to take it further and see more in differences and discrepancies between the platforms.
Yep. And actually, we have a couple of minutes, so I have more question. This is something that it was not clear from the paper and from the presentation. Do you also, like the fuzzer is also simulating the physical signals from the real environment, or is only simulating network interaction?
So the inputs are actually just passed as like a memory buffer. Okay. So when the program is compiled, it has like an entry point function that has all of the inputs defined, and it's just a byte struct, and so you can pass it in however you want.
Yeah, but these inputs are like representing physical signals that were supposed to be taken from sensor, right?
Exactly, yeah.
So are you also modeling the physical world so that the input makes sense, or you expect the attacker can literally do everything with these sensors?
You would need to modify the harness a little bit, so that's a good point. Some of our harnesses include like a function that ensures that inputs have to be ASCII. because some functions, it doesn't really make sense to accept any byte. And so that's something that's a little bit more like function specific, but is definitely something that we consider and would be future, like a area for future research to look more into.
All right, thanks again. Let's do another round of applause for our speaker.